Hi everyone. So today we're going to take a look at functions that are inverses of each other and talk about what is the relationship of the derivatives of two functions that happen to be inverses. So we are going to start by reviewing a little bit about inverse functions. I'm actually going to use a graph and a diagram to kind of help me with that. So if you want to jot any of that down in the section where I've left you for review of inverse functions, you're welcome to. We're just going to remind you of a couple of things you need to know from algebra about what it means to be inverses. Okay, so here we have two functions that are inverses of each other. And we're going to use these to kind of remind us how inverses work. So we're going to start with just this plain old x squared. Everyone should recognize that one. That's just your plain old parabola, right? The inverse, the goal of an inverse is to take all of the xy pairings and reverse them. So this function we could technically, and I shouldn't say that, it's not really a function, but this relation I could get away with saying is x equals y squared, because that's what an inverse does. It reverses the x and the y coordinates. Now, back in algebra, we very rarely let you get away with writing it like that, right? We'd solve it back for y, and we'd have to take a square root on both sides, which means we would need a plus or minus in here. So we would say this is plus or minus square root of x. And so the idea here is that if I took a value and squared it, and then took that answer and put it in over here, it would return us back to where we started. So that's what inverses do, is they reverse course. They take the output from one function and revert it back to its original input. Okay. So there is one graph quality that is important to know, important to remember here, and that is that when two functions are inverses of each other, they are reflections over the line y equals x. So I'm going to try to do this and keep this line straight. But this diagonal line y equals x, if I were to fold this graph on that black diagonal line, the red graph would lie right on top of the blue graph. So I'm just going to make a note of this down here, that this is the line y equals x. And so when you cross over that line, what is happening is your xy coordinates are reversing. Okay? So, for example, if I go back to my original y equals x squared, sorry, I'm trying to center that for you. I could pick a point on here. I don't want to pick one where this intersects, so I'm going to take like this point right here. This is the point 2 comma 4. If I were to fold my graph on this diagonal line here, and think about where this 2 comma 4 is going to end up, it would end up right here at the point 4 comma 2. And so what you'll notice happened is your x's and y's switched positions, right? 2, 4 became 4, 2. That's what happens under an inverse. So when we're talking about, derivatives, and we're talking about the relationship between these functions, this is how we're comparing our points here. We're not comparing like a 2 with a 2 down here. We're comparing this x value of 2 to this y value of 2. And so we're constantly going to have to be switching back and forth between what is x and what is y. So now let's talk about what happens with the actual derivatives. And so again, I'm going to zoom this in some, because we're going to draw some tangent lines in here. If I wanted a derivative, I would need a slope of a tangent line, and my tangent line is going to look something like that. Now, if I did a better job drawing that, we could probably just count rise over run. But we don't need to do that because we know how to calculate derivatives. This is an x squared function, right? So the derivative would be 2x, which means when x equals 2, my slope should be a positive 4. Now, I'm going to write that as a 4 over 1, and you'll see why here in just a second. When I go to talk about this derivative, I want you to notice what this slope looks like. It looks something like this. And so if you think about what's happening when this line is folded over, right? When this purple line gets reflected over this line like everything else does, the exact same thing is going to happen. The x's and the y's are going to switch positions. And what that means for us is that my top and my bottom of my slope are going to switch positions, right? Because these are your y values up on top here, and these are your x values down here. But anytime I fold over this black line, x and y reverses. So this slope would be a 1/4. So it's a reciprocal of what my slope was a minute ago. Okay. And we could verify that. I mean, we could come in here and say, all right, let's find our derivative. Our derivative is going to be, 1/2 x to the negative 1/2. In other words, we could say it's 1/2 square root of x. And so we're finding that at x equals 4. So if I put a 4 in right here, I would get a 2 times another 2, and there's my 1/4. Okay, to show that that derivative would be 1/4. So the point here is that these 2 points have slopes that are reciprocals of each other, but that relationship between the points is important as well, that the x and the y are reversed. So let's go back to those examples we were talking about. Okay, so when we're talking about our inverse functions here, and let me just slide this up some. If the original function matched up a to b, what that's really saying is that the original function had the coordinate a comma b, then under the inverse, so that f negative 1, that's the inverse notation, what would end up happening is the b value would get matched to a. Or in other words, we would have the point b comma a in the inverse function. So if the derivative at a is m, okay, then what we would know is that the derivative at b in the inverse function, and this is hard to write. This is, it's going to look something like this. It's going to look like f negative 1 derivative at b would be the reciprocal of that, which is 1/m. I actually think that sounds a lot more confusing than, some of the problems we're going to do. But basically the derivative of the inverse, we have to look at point B instead of point A, and then we have to do a reciprocal of that derivative. Okay, so let's head down here. Like I said, I think once we get some numbers in here, this will make a little more sense. If f of 0 is 1 and g is the inverse of f, write a relationship between f prime and g prime. And even this doesn't have a whole lot of real specific numbers to it. But if we know that f of 0 is 1, then we also know that g of 1 is equal to 0. Okay, that's how inverses work. That's using the fact that these two things are inverses. But we want to talk about derivatives, right? So we could say for the derivatives that if I wanted to do f prime of 0, let's just say, because that's my x value in the f function, what I would actually have to do is find g prime of 1, because that would be the x value in the g function, and do a reciprocal of it. Okay, I left kind of a lot of space here. And we'll just make it a really big equal sign. But if I was trying to find the derivative at 0, and I didn't have enough information to just find the derivative at 0, if I had a way to find the derivative of this other function at 1, because these two things come from that inverse relationship, I could do a reciprocal of that derivative, and that would be correct. I guess I could also say, just as another option, if I wanted the derivative at 1, I could do 1/g prime of 0. Okay, let's take a look at example 2 here. So let f of x equal blah, blah, blah. This statement right here is just telling me that these two functions are inverses. And I want to find the derivative of g at 1. Notice I don't actually have the g function. Now, in this one, they did give me the f function. Sometimes they don't even give you that. But we could go find the g function. I wouldn't recommend it. I don't think we need it. I usually approach these problems kind of in 3 steps. And so the first step is to say, if we want the derivative at 1, but all I have is the f function, I need to know f of what number is equal to 1, because this 1 is going to be like the y value in the f function. So I'm asking myself this question. Okay, important to understand that this is a question I'm asking myself. What x value would give me a 1? Well, let's see if we can figure that out. Okay, here's my f of x, 2x plus 1 cubed, and I want this thing to equal 1. And we could do a good amount of solving here. I'm hoping that you can just kind of look at this and reason your way through it. But we could take, a cube root on each side and then subtract 1 and divide by 2 and all that stuff. But what I'm hoping you see is that I would need this thing to equal 1, right? And since this is already a plus 1, what I really need is for this to zero out. I need x equals 0. Okay. Because if x were to equal 0, then my f of x would equal 1. So this is the x value that I'm now targeting when I go to take my derivative. So my second step is then to find my derivative at 0. Okay, so what is my derivative at 0? Okay, so I'm going to need a derivative of this thing. So let's try f prime of x. I'm going to need chain rule here, right? So I'm going to start with a 2 times, and now I'm doing a derivative of my cube. So I would say 3 times 2x plus 1, bring down that power. So this is now a square. So this is 6 times 2x plus 1 squared. And now I need specifically that derivative at 0. So 6, 2 times 0 plus 1 squared. Okay, so this whole thing just becomes a 1. 1 squared is just 1. And so I think my final answer here is just a 6. And my third step here, to actually answer my question, and I could have actually jumped to this third step a second ago. I would still have to come back and do that thing in the middle, but I could say, I know that g prime of 1 is the reciprocal of the derivative at 0, right? That's that inverse relationship. So now I know that value, right? I know that f prime of 0 is equal to 6. So I can say g prime of 1 is equal to 1 over 6. Okay, I did rush through that one just a little bit because I don't think those ones where you're having to solve, so the ones that have a step like this where you're having to solve to find your x value are all that common. Honestly, this is algebra, right? And again, we're not testing your algebra, we're testing your calculus. So I think ones like this example 3 are way more common in calculus land. Okay, so I want you to just look. They've given you a bunch of information about g. They haven't told you anything about h. They're only talking about g. Yet somehow they're asking you to find a derivative of the h function when we know nothing about h, right? So here's how we're going to start this, because we do know one important thing about h, and that's that h and g are inverses of each other. So I can use all of the stuff that I know about inverse functions. Remember that if 6 is an x value in the h function, then it's a y value in the g function. So that's what I have to figure out first, is what is the x value that should be matched up with the 6? I'm asking myself this question. What is this x value that would match up with 6? So take a look at the list of values that you're given and see if you can answer that question for yourself. And it really is kind of just sitting there for you. But right here I can see that g of 3 is equal to 6. So I found my magic x value. Okay. And that's important because so in the g function, we have the coordinate 3 comma 6. In the h function, that same coordinate would be 6 comma 3, right? So if I'm trying to find this derivative, I need to know where to start. I need to know that I'm looking in the g function when x equals 3. And that actually tells me, if I jump way over here to the end of my process, it tells me kind of how to find my answer. I still am going to have to do a little bit of work, but I know that my derivative at 6 is going to be the reciprocal of my derivative of g at 3. Okay, so I know that relationship is true because under my inverse, the 6 and the 3 are paired up together. Okay, and because it's an inverse, my derivative is going to be a reciprocal. So let's fill in that middle step. The middle step is, can I find g prime of 3? And sometimes you have to actually work for this, right? But this time I think it just gives it to me. Let me finish writing here. Oh yeah, right here. So g prime of 3, they're telling me right here is -2. So question answered. G prime of 3 is equal to -2. And so my answer here for h prime of 6 would be the reciprocal of that. It would be 1 over -2. So kind of 3 steps. First of all, figure out what x value it is that we're targeting. Second step, find the derivative at that x value. And then third step, take a reciprocal of that. Okay, so you have to find the x value that pairs up with this as a y value. Find the derivative there and then flip it over. Okay, on to some more examples. Let's zoom this in. Okay, once again, you've got that magic piece of information that g and f are inverses of each other. Notice it's asking you to find g prime of 4, and conveniently they've left off the column that would tell me anything about g prime. Love it when that happens, right? But the question here is that if in the g function, a 4 is an x value. So in the g function, we have 4 comma something, right? I'm trying to find the derivative at 4, but I don't have any information about the derivative of g. So I need to go look at the derivative of f. And in the f function, this would be my x value that I care about. So I need to figure out what is that x value. So again, that's my step number 1, right? I'm asking myself, in the f function, f of what gives me that 4 as an output? Okay, so let's look in my f column here. Where do I see 4 as an output? I see it right here when x is -2, okay? So I was just able to solve this and say, all right, this happens when x is -2. What that's telling me is that in my g function, my y value would be 4, -2. And in my f function, I would have the point -2, 4. So I'm doing this because I don't know anything about what's happening at this point, but I can figure out what's happening at this point, and I know that these two are related. So at the end of my problem, I already know that when I go to try to find g prime of 4, that's going to be related to the derivative of f at 2. It's a reciprocal, so it's 1 over f prime of 2. Question now is, what does that f prime of 2 look like? Right? That's pretty easy though, because I have f prime here, right? Oh, I'm so sorry. This is a -2. Where did I screw this up? This is a negative. This is a negative. I had it right up above, but okay, so sorry about that. F prime of -2 is this value right here. Oh, it's also 4, just to make that nice and confusing. So my f prime of -2 is 4, which then I can fill in over here and say, all right, fine then, g prime of 4 is 1 over 4. It's a reciprocal of that derivative that I just found. Okay, one last example here, and I'm trying to decide if this is one that I have to solve again. Kind of looks like I might. Maybe not. Maybe they gave me what I need. Let's find out. Okay, so we're trying to find the derivative of g at 2. And of course, once again, they didn't tell me anything about g other than the fact that it's an inverse of f. Okay, so my first step is to ask myself, f of what x value gives me that 2? Because again, this would be the x value in the f function, which is what I need to use to find my derivative. So f of what makes 2? Oh, hey, look. They told me this right here. F of 1 makes 2. Okay, so this is x equals 1. And so that tells me right away that at the end of my problem, I'm going to be able to say g prime of 2 is the reciprocal of the derivative at 1, of f prime of 1. But my big question mark now is just, what is this? What is f prime of 1? Okay, so this is where our solving is going to come in, because it didn't tell me what f prime of 1 was. So that's where my next mission comes into play. I'm trying to find what is f prime of 1. Okay, that's old news, though. You guys can find f prime of 1. We just need a derivative, right? So I guess let's start by finding our actual derivative. So this is 3x squared plus 1. I want f prime of 1. So that's 3 times 1 squared plus 1. So that's 3 plus 1, which is 4. And now that's what's going right up in here. And so I would answer this question by saying g prime of 2 is the reciprocal of the derivative of f at 1. So it's 1/4. So that's all there is to this. And I know it sounds complicated, but it's these same 3 steps every time. That first we're trying to figure out what is that magic x value that pairs with this y value, because that's where I want to take my derivative. And then once I find that derivative, I want to do a reciprocal when I hop back over into the other function. So we're going to give some of these a try tonight. You'll get good at this relationship the more times you do it. And if you have questions, as always, please feel free to ask.